Welcome to video M17B on the cost of quality. So there are two ways of measuring quality. And we're going to deal first with this idea of a goalpost. So goalpost conformance assumes that the firm incurs no quality or failure cost or loss if the quality measures fall within specified limits. For example, confirming that each beverage has the proper mix of ice and beverage. Too much ice, complaints about not enough to drink. Not enough ice, complaints about drink not cold. However, very few customers are going to count the number of cubes, so there's some tolerable range that is acceptable. However, absolute quality conformance requires that all products or services meet exactly the target value with no variation allowed. Any variance from the precise measure is thought to add some form of loss to the product or service. If I have an appendectomy, I pretty much expect the surgery to be 100% effective. Any deviation, for example, a post-surgical infection or leaving a scalpel in my belly, is likely to be viewed as a quality loss, and frankly a visit from the malpractice lawyer. Because an absolute measure implies a loss with any deviation, a loss function can be used to estimate the loss associated with the deviation. Before we do an example, let's deal with some of the terminology. The loss function of X characteristic is equal to the total quality cost divided by the tolerance permitted squared, or in other words, the variance of the characteristic. There's pretty much no way to understand this without doing an example. So a company manufactures a cylinder that is designed to fit inside a sleeve and has received an order for 50,000 cylinders at a price of $80 per cylinder. On average, it costs about $50 to manufacture a cylinder. The perfect fit is a cylinder of exactly 1.275 centimeters in diameter. However, the cylinder will still function if the diameter is between 1.25 centimeters or 1.30 centimeters. Any smaller or larger than those thresholds, and the cylinder must be replaced at a cost of a new cylinder, which is another $50, plus expedited production and shipping, which adds $20 for a total of $70. Our manufacturer generates 80 cylinders and decides to take a measure of the cost of quality, or think of it another way, the cost of the lack of quality. This table presents the results of the production run. The smallest diameter cylinder was 1.232 centimeters, and the largest was 1.32 centimeters. You can see the frequency of each diameter cylinder produced as well. The good news is that the highest number, 18, were produced exactly to spec. Now we can use this information to determine the loss function with respect to diameter. To start with, the total quality cost is the cost of the original cylinder plus the cost of the replacement, or $120. The tolerance permitted is either 1.75 to 1.25 if it's too small, or 1.30 to 1.275 if it's too large. Either way, it's a 0.025 difference. If we divide the total cost by the square of the difference, the total cost is $192,000. Okay, now we need to analyze our production run and see how our production matches up with our loss function. The easiest way to do this is probably in Excel. So here we go. Okay, here we are in Excel. And you can see that what I've done is I've taken that table of cylinders that we produced in our 80 unit run and put them into a table with the smallest diameter at the bottom and the biggest diameter at the top, and the frequency of each one of those diameters produced. Okay, so now the next thing we do is determine what is the probability of having a cylinder of each of these diameters. And that probability is pretty easy to find. It's just the number of units at that diameter divided by the total. So that gives us the probability of getting each size of each one of these. And you can see again, one of our highest probabilities, the highest probability, is to hit the mark exactly, which that's good news from a production perspective. And then we can calculate the per unit loss function. So the per unit loss function is the diameter minus our targeted diameter squared times 192,000. So we can do that for each unit. But what that doesn't consider is what is the number of units we made? Or better, maybe a better way of saying it, was the probability of making a cylinder of that size. And so we calculate instead a weighted average loss function. You can see that the weighted average loss function is the per unit multiplied by the probability. And we total those and determine that our per unit loss function is about $36.45. But we're not done yet. So the next thing we do is calculate the weighted average diameter. So that's take the diameters that we measured. What is the weighted average, not the simple average, but the weighted average. And you do that by calculating the diameter times the probability of having that diameter. And you just add them up. So the mean weighted average is 1.27565. So pretty close to our expected value of 1.275, but not exactly right on it. And of course, we have some variance around that mean. So the next thing we do is calculate that variance around the mean. So there is the distance from the mean squared, right? So that's simply the diameter minus the mean, and that difference is squared. And then lastly, what we do is we take that distance from the mean and multiply it by its probability. So they can get the weighted average variance from the mean. And looks like we need to expand our column a little bit. And there it is. There's our weighted average variance from the mean of 0.001894025. So a couple of these things we're going to need to remember as we go back to the slides. Our weighted average loss, our weighted average diameter, and lastly, our weighted average variance. Okay, back to the slides. Okay, so now we can calculate the expected loss per unit. So the expected loss of X equals K times the variance squared plus the average diameter squared. So we know that K is 192,000. We had calculated that previously. There's that variance squared. That was the last column we calculated. So that's 0.0, the weighted average variance squared, 0.001894025. Then we calculated our diameter average minus our expected average was squared. And we simply now can do a little bit of math. 192,000 times the variance squared plus the diameter squared equals $36.45. Okay, so that's called the Taguchi loss function. All right, the last thing we're going to cover with respect to cost of quality is this idea of segregating quality for cost analysis. And as usual, we know that we want to deal primarily with quality-related costs that are relevant. So most accounting systems, unfortunately, are not built to identify various quality-related costs. A review of a typical financial accounting chart of accounts is probably not going to reveal a large number of accounts that track just quality-related costs. As a result, these often have to be segregated for use in quality control. Typically, quality costs can be segregated into 4 buckets. Prevention costs, which are the costs, of course, to prevent defects in the first place, such as training for employees or keeping the equipment maintained and in top working condition. A second area is appraisal costs, which are the inspection and testing costs associated with various stages of the process. A third area of quality costs is internal failure costs, such as the cost of scrap, rework, or an additional inspection cost. And lastly, external failure costs, such as returns by customers, warranty costs, canceled orders, or lost customers are also a concern. Like our other analyses, a relevant cost structure can be used to determine whether a quality enhancement will work. For example, P&G is a package delivery company and feels that customer perspectives on quality lean heavily on three areas: delivery time, which is the time it takes to get the package there; being on time, which is making sure you deliver the package by the time it was expected; and of course, lost or damaged packages. P&G is considering a new technology that will cost $80,000 per year, but is expected to improve some of these measures. Here are the current measures of quality and the expected measures if the technology is put into place. You can see that the on-time delivery rate is expected to increase from the current rate of 80% to the new expected rate of 95%. The variable cost per package damaged or lost will remain at $30 per package, and the allocated fixed cost per package damaged or lost will also remain at $10. But the number of packages lost is expected to decrease from 300 to 100 with this new technology. We should also note that each percentage increase in on-time delivery should result in an additional $10,000 in sales. And P&G's average contribution margin ratio is 40%. So now we need to perform a relevant cost analysis to determine whether P&G should invest in this technology. Since we are expected to have a 15% increase in on-time deliveries from 80% to 95%, sales would be expected to increase by $150,000. The new technology is going to cost $80,000 a year. The new sales that we generate will, of course, continue to cost a variable cost of 60% of each sale, as indicated by the 40% contribution margin ratio. However, the reduction in lost or damaged packages will reduce costs by 200 packages times the $30 variable cost per unit, or $6,000 worth of cost savings. Unfortunately, the net result is that the new technology will cost $14,000 more than it will create in sales and cost savings each year, and on this basis, it should not be placed into service. However, financial measures alone should not be the only thing considered. Non-financial measures, such as those presented here, certainly can almost matter. And some version of this type of data or information would always find itself onto a well-designed balanced scorecard. One last topic before we close out Chapter 17. Process cycle efficiency, or PCE. Many of the internal measures we just looked at involve in some way the efficiency by which the production cycle is completed. PCE provides a simple comparative measure of process efficiency. Recall our previous example involving the McDonald's drive-thru. If the making of the burger, fries, and the drink is the processing time, PCE would help the business examine the non-value-added time, so that the focus can be on what counts the most. PCE is simply the value-added time divided by the total time, and the total time is value-added time and non-value-added time. The closer to 1 the PCE becomes, generally the better, but we will see that that is not always the case. If Carnac Company has 2 locations that manufacture the same product, and they examine the time to complete a product in each location, step 1 is to identify the time spent in the total manufacture of the product. For this product, that is setup, moving, waiting, inspection, and of course the actual processing of the product. Average measures of these are taken at both locations, and the non-value-added times are aggregated. The PCE can be calculated as the processing time divided by the total time. And we can see that the West PCE is closer to 1. However, should we choose the production process in the West over the East? 2 things bear closer examination. Number 1, if the quality of products is the same, the East has a much quicker processing time for the product, 60 hours versus 80 hours. This would allow Carnac to focus its attention on the non-value-added times and really try to reduce them to become more efficient. That's the end of video M17B. We start chapter 18 next. We're getting through this.